Hello everyone, I am Narciso and I will be presenting our research entitled On Polynomials Associated with Peaks of Dyck Left Factors. This research is a collaboration with one of my supervisors, Dr. Paul Vary from SCTU Ireland. We begin this discussion by presenting some preliminary concepts related to the research. First, we have Dyck paths and its left factors. So a Dyck path of semi-length n or length 2n is a sequence of 2n plus 1 points in the first quadrant of the integer lattice Z2 that carries the following properties. First, the initial point is at the origin, while the terminal point is somewhere along the positive x-axis. While if you select two consecutive points, then they exhibit a specific step being used. In a Dyck path, there are two steps. We have the up step and the down step. So for example, we have a Dyck path here of semi-length 10 or length 20. A Dyck left factor, meanwhile, of length n is the beginning portion of a Dyck path, or sometimes referred to as the incomplete version of a Dyck path. That is, the terminal point may or may not lie along the positive x-axis. So if the terminal point lies exactly somewhere along the x-axis, then the Dyck left factor becomes a full Dyck path. If it is not, then it is simply a Dyck left factor, a proper left factor. So as an example from our Dyck path earlier, we have its left factor that ends at 14.4. Dyck paths are counted by Catalan numbers. That's a well-known fact. And its generating function, of course, that's also well-known. While Dyck left factors are counted as A001405 in the OEIS, where its nth number is the maximum coefficient of the binomial expansion x plus y to the n. While its generating function is given in equation 4, and you can perceive here that it is somehow dependent on the Catalan generating function. Next, we go to the Narayana numbers and polynomials of the second kind. We define a peak of a Dyck path as the pair of up and down steps in its sequence of steps. So, for example, from our Dyck path earlier, it has 5 peaks, and if you look upon the sequence of steps, if you trace the pairs up and down, then that precisely corresponds to the diagram of 5 peaks highlighted by blue. The Narayana numbers of the second kind, defined in equation 5, counts Dyck paths of semi-length n and with k peaks, where n and k are non-negative integers. Now, this is not the standard Narayana numbers that you would see in, say, Wikipedia or other known combinatorics textbooks. But this Narayana version includes the trivial path. So that's why we start from n equals 0 and k equals 0. And it is registered as A090181 in the OEIS. Well, if you look at the first few values, if you delete the first row and first column, you retrieve the standard Narayana numbers. Only that we include in the counting the trivial path. While the Narayana polynomials of the second kind is defined in equation 6, where its coefficients are the Narayana numbers of the second kind. And its generating function, phi sub 2 xt is defined in equation 7, and this is also the bivariate generating function for the Narayana numbers of the second kind. Now, take note of this generating function because it will be used continuously later in the results. The question here now is, will there be an analog for Dyck left factors? Well, the short answer is yes. In fact, one can find a family of numbers defined in equation 8 that counts the number of Dirichlet factors of length n and with k peaks. Here we denote this by p sub 2 and k. And it is listed as A124428 in the OEIS. And its first few values are shown here in the table. And take note that it is not a perfect infinite lower triangular matrix, but it is somehow vertically stretched. And we define the corresponding polynomial for those numbers, and that is script p sub 2n. That's the polynomial associated with peaks of Dirichlet factors. The problem now is we don't know the exact generating function for these polynomials or even the bivariate generating function for the numbers earlier. So to solve this problem, we will use the Riordan arrays. What is a Riordan array? Well, a Riordan array is an infinite lower triangular matrix such that the generating function of the kth column, where k is non-negative integer, is g times f raised to k here, where g is a formal power series of order 0, while f is a formal power series of order 1. Okay. The notation now is the pair G and F. And a little bit of history now. Riordan arrays were discovered by Shapiro and company by observing the Pascal's triangle, because the anti-diagonals of the Pascal's triangle has a pattern in terms of the generating functions. It follows that the generating function of the kth column is x over 1 minus x raised to k. That's why the Pascal's triangle is the most classic example of a Riordan array. And we collect the Riordan arrays and denote the collection by script R and define the binary operation on script R in equation 11. The binary operation here imitates the usual multiplication operation for matrices. It's just that we need to observe the definition of a Riordan array. And so the definition for the binary operation goes like that. Then the pair, script R and star, is the Riordan group with its identity element 1 and x. And for any Riordan array, the inverse rather, is given in equation 12, where f bar is the compositional inverse of f. Take note that the compositional inverse of a formal power series only exists if the power series is of order 1. And finally, we take note of the fundamental theorem of Riordan arrays, which says that the Riordan group acts on the ring of formal power series by the action defined on equation 13. Now, this action simply imitates the matrix vector product of, as well, you can see in linear algebra, because you can interpret these as matrices and vectors as well. And if you set our generating function u as the generating function with coefficients all ones, then you can get the generating function of the row sums of the Riordan array as shown in equation 14. And our goal here now is to apply Riordan array techniques to obtain the polynomials, the generating function of the polynomials associated with Dirichlet factors. So we go now to the results. We need this lemma. This actually says that any Catalan type generating function can be converted as an action of a Riordan array to the Catalan generating function. So this will be useful later on to extract coefficients. And our candidate for the generating function for Dirichlet factors, okay, our candidate generating function is defined in equation 17. Well, we can prove this by analyzing the first return decomposition of a Dirichlet factors with respect to peaks, and then apply the symbolic method. Okay, so these are the four decompositions, all right? And using the four decompositions, we arrive with this functional equation here. Take notice of the use of the Narayana polynomial generating function earlier. Well, that is evident because in the fourth decomposition, we use a non-trivial Dyck path. So in the end, we use this generating function phi sub 2. Only that it is A-rated because the counting for Dirichlet factors is per length, not by semi-length. So by rearranging and then simplifying, we prove that our candidate generating function is an action of a Riordan array to the Catalan generating function. And by using the FTRA, the fundamental theorem, setting G sub n of t as the coefficient of our candidate generating function, then G sub n has this explicit formula. Our goal here is to simplify this explicit formula here, okay? That would match the polynomial associated with Narayana, the polynomial associated with Dirichlet factors peaks. And to simplify that, then we use these two identities here. The first one is a little bit common, while the second one is known as the alternating van der Monde identity. And finally, we prove that G sub n is simply the polynomial associated with peaks of Dirichlet factors. And this also fully confirms that phi sub 2 LF, our candidate generating function, is in fact the generating function for polynomials associated with peaks of Dirichlet factors. That's the first way. An alternative approach is via a direct Riordan array construction. But to do that, we need to take note of the convolution of Narayana polynomials of the second kind. In the paper of Barry and Hennessy, they prove that the Narayana polynomial is the coefficient of x to the n plus 1 of this generating function here, where the reversion operator spits out the compositional inverse. So by applying Lagrange inversion on the right-hand side of equation 23, we get the convolution formula for the Narayana polynomials of the second kind. Now, we will construct the Riordan array associated with the polynomials. Let h sub k be the generating function for Dirichlet factors, which ends at level k. Now, if k equals 0, then we simply obtain the generating function for Narayana polynomials of the second kind, except that it is A-rated, again, because we're counting by length. And if k is positive, that this is greater than or equal to 1, sorry, then we have three specific decompositions. This is somehow related to the decompositions earlier. And take note of the use of the non-trivial Dyck path there, so that we have this recurrence using symbolic method in equation 26. And by having the fact that h sub 0 is the generating function, the A-rated generating function of the Narayana polynomials of the second kind, then we obtain the explicit formula for h sub k in equation 27. And by using h sub k as the generating function of the kth column of a certain Riordan array, then we obtain the specific Riordan array in which the generating function of the row sums is exactly the generating function for polynomials associated with Dyck left factors. And that is actually our next result. We shall describe the entries of this reordered array. All right. The main diagonal is all ones, while whenever the n case entry is n minus k is odd, then that automatically becomes 0. And if n minus k is a positive even number, then its n case entry is in equation 29. In fact, our reordered array is an example of a checkerboard subgroup. A checkerboard array, member of the checkerboard subgroup. And by taking the row sums of this reordered array, all right, using the formula in equation 29, then we can get an alternative form of the polynomials associated with Dyck left factors as defined in equation 30. Now, we define our polynomial with respect to Narayana polynomials of the second kind. And moreover, it is a convolution, a specific powers of the Narayana polynomials. So that ends our presentation, and thank you for listening.